considerations, and mechanisms. By the end of this module, you'll be able to use queues for inter-process communication and sending messages. Let's review a little bit about queues. Queues are one of the most popular methods in LabVIEW for transferring data between two different locations on your diagram, typically between loops. The way this is done is you will obtain a queue to obtain a queue reference. That queue reference can then be used to either enqueue elements or dequeue elements. Typically, you'll have one loop enqueuing elements that will be producing data, and you'll have another loop that will dequeue elements, which is consuming that data. When obtaining the queue, it's necessary to select the data type that the queue will hold. You do this by passing a constant or control of that data type to the data type input. In the case that we see here, this will be a queue that contains a string. It's also possible to provide queues with names. In this way, you can provide a name such as main queue, and elsewhere in the program, also call the obtain queue function with the same name and get a reference to the same queue in memory. Be careful, as this essentially makes that queue a global resource because somebody else or some other location within your program may be able to obtain a reference to it and potentially change it. The alternative, and again it's a trade-off, is to simply pass the queue reference into the other function. Personally, I typically will not use a named queue, but rather pass the reference around, because then I have control over who has access to my queue. Your mileage may vary, your application needs should dictate what you choose. And notice that on the adding elements to the queue graphic, we're passing an element of message 1 into the queue. That will be the same thing that comes out of the dequeue element function on the bottom portion in the element control. And there's also a number of queue operation VIs that you can use to work with these queues. We'll talk about some of them as we go. One of the most useful ones to keep in mind is the lossy enqueue element. This will essentially allow you to create a circular buffer such that when you add data to the queue, old data will fall off the front if the queue is full. Similarly, we also have the enqueue element at opposite end, that is near the bottom of that palette. This will allow you to put a message on the front of that queue. It's very often used for an emergency shutdown, a stop, a safety condition, such that you don't have to wait for any queued up commands to execute before going into that state. Continuing with the theme of review, here's a basic producer-consumer with events pattern. You'll notice that we have two loops, the upper loop, which is the producer loop, the bottom loop, which is a consumer loop. The upper loop is going to enqueue elements based on user interaction. There's an event structure there that will fire different cases depending on what user action was taken. Typically, those events will correspond to data enqueued onto the queue, such that the consumer loop will take a different action. So, for example, rather than saying element, we might send a command down to the consumer loop, such as run RT code or stop RT code, something of that nature. What we'll typically want to make sure of is that we have a good division of labor within the system. The goal of producer-consumer with the events architecture is to efficiently respond to user interface interaction, even if we're busy processing some previous request. To do that, we're going to divide these commands into categories. A producer loop should only handle things that can be handled immediately, something that will not introduce a delay if the user keeps interacting with the front panel. The consumer loop should handle any extended processing, anything that takes more than a very short period of time, on the order of milliseconds. And the linkage between these is again a queue. Hopefully you've seen this pattern in use many times already. We'll put it to use again here. One of the more common usages of queues in producer-consumer architectures is to send messages. A very scalable method for doing so is to not send a simple data type such as a string or a numeric or a boolean, rather to pack the data into a cluster. That cluster would contain what command we wish to send, represented by either an enum or a string. In this case, you see run recipe as the command, and then either a variant or sometimes a string to handle any data associated with that message or command. So why a variant or string for that portion? The reason is that a variant or a string are the two data types in LabVIEW that can hold any type of data. Any other data type can be converted to these two. In this example, we're using variants, and that's what we'll use in the course project. Strings are also an option. Use the one that makes the most sense for your application. In this exercise, we'll get some experience using a queue-based messaging architecture to create a user interface VI that will communicate using queues. Let's take a look at the solution to exercise 3.2. In this exercise, you built out the queue message handling for the user interface. Let's open up the user interface VI and take a look. So when we run this, let's see what we've built. Previously, there were just buttons on the front panel, but they didn't really do anything. Now when I press the buttons, we'll see that the system status reflects which button I press. Let's see how we did that. Let's go to the block diagram. What you'll see is that we've added some queue elements here that will handle the message communication from the event handling loop down to the UI message loop. We're using a UI data control. If you notice, based off the triangular glyph in the corner of this constant, this is a type def. This is going to be very critical when you're dealing with things in different loops, potentially different VIs in your system, that you type def your data types in this way, such that if you change your mind or you decide to make a change, you only need to make that change in one location. I highly recommend type defing any clusters that you use as queue elements. It'll make your life a lot easier later. What's in this cluster is a string message and a variant data. As we mentioned before, messages are very often going to be of a fixed known type, so you can either use an enum or a string for that, and for the data field you could use either a string or a variant. In our case, we're using a string for the message and a variant for the data. You can make other choices, just make sure you're making an informed choice. Also setting a maximum queue size, such that if our queue gets full, anything else trying to be added to the queue, we'll have to wait until the queue gets emptied. This can keep our system from sending too many messages and expanding memory too fast. First, we're going to send an initialize message with no data associated with it via the enqueue element function. Any messages are going to show up here, this dequeue element function. Notice that no timeout is wired, so this loop will wait as long as possible or as long as necessary to get an element off of that queue. Let's scroll over. For each of the cases of our buttons on the front panel, we now have a value change event, and for each of those events we're going to send the appropriate message down to the queue. Connect controller sends the connect event. Run control sends run control. Stop control sends stop control. We have very creative names. Typically we're going to want to make those names as obvious as possible so it's very easy to tell what's happening in the system, especially because you might not be the person who owns the system in the future. Keep your support burden as low as possible by making the code as well documented as you can. This is a good way to do that. So if we send a connect to controller message, we'll send connect. Send it down here. We will dequeue and see what type of message did we get. We got a connect message. I'll send connect. That's the system status. System status was the text field on the left side of the screen that we saw when we were running this VI earlier. Right now this code doesn't really do much. It doesn't actually connect to the target. It just says that's what it should do. When you're building out this type of architecture, this is a really good way to prototype things and make sure that you got all your cases correct before you start adding in code that could actually affect the system. I usually do it this way to make sure I didn't make any silly mistakes and to quash those bugs as soon as possible. Something else you can note is we have not yet wired this data field to this case structure. We're not doing anything with that data. And so far up here, we've also not wired anything to the data field of the cluster. We'll do that later as we continue to add more features to our project. Also, if there's an error that occurs in the event handling loop, we will send an exit message to the lower loop to let it know that something has gone wrong and we should stop execution. If your system does not have a method to stop execution, you're not yet done building out the framework for your system. I highly recommend getting the system able to. In the previous section, we used queues for inter-process communication and sending messages. By the end of this module, you'll be able to describe how to use the Asynchronous Message Communication, or AMC, reference library for inter-process communication. The Asynchronous Message Communication, or AMC component, is a library created by NI System Engineering Group to permit sending of messages between processes on a local target or between different targets using a very similar API. It's inter-process communication based primarily on queues under the hood, but with some usability tweaks, primarily the ability to keep the same look and feel for both the inter-process and inter-target communication. You can download the AMC reference library from ni.com or use the installer that's included in the exercises folder of this course. AMC provides a very good set of libraries for quickly building up a messaging system with much of the plumbing done for you. AMC also provides a number of templates and examples to get you started quickly. Let's take a look at an example of the Asynchronous Message Communication library in action. Here's a simple project I created that contains the AMC simple clock example that ships with the AMC library. Let's open it up. And we'll give it a run. What you'll see is that the clock updates once per second, and that's going to happen on a periodic basis without any user input necessary. We also have the ability to respond to user events within the system, such as changing the clock style from analog to digital, clicking an About button, which will give us a dialog box, or saving the state of the system so that we retain our last clock style when we run this again. And we now save this state. And just for fun, we also included a binary clock style, which will make you the envy of all your friends in the office. Let's take a look at how this operates. But first, let's go back to a normal clock. Here's the block diagram, and we're going to start off just on a high level. We have two loops. This is the message generator loop. This is our user interface event handler. We have an event structure that handles each of the buttons on the screen and performs different actions accordingly. This is going to look very similar to your producer-consumer with events pattern, and essentially it's performing the same end goal. Take user input, send that user input as commands into the other loop. The other loop is our message processor, and this is where we will dequeue elements from this queue, decide which message came in, and based on which message came in, take a different action. So we can update the clock style, we can set our internal state. Notice over here, this VI that we're using, this is the AMC read next message VI. What it's doing is letting us know the message name and message value as well. Basically, this is a combination of that cluster with an enum and a variant or a string inside that can take the command and any data associated with the command. Same thing here, except this does all the parsing for us and we don't have to worry about queuing or dequeuing the actual cluster and then bundling and unbundling the cluster. Here we just pass values in through this API and that's done for us. Let's take a look at how we pass those in. Over in the message generator, we can send a local message, so long as we provide it with the message queue and the name of the message that we're sending. Optionally, we can also provide it with some message value, data payload to bring with it. This library is also nice because it gives us the ability to send these priority messages, which we'll use an enqueue at opposite end to put the message at the very front of the queue. Here, let's take a look at the About button. If you press the About button, we'll send the About message. Since the same queue reference is shared between these two loops, pressing the About button will send the About message, which will execute the About case here. And that's where we got our one-button dialog with the About information. Creating the queue is done here. AMC create message queue. Give it a name, in this case, the name of our VI. And then we can also optionally provide it with some initial messages, basically providing some initial data for that queued message handler to chew on. Typically going to include an initialization case, and sometimes reading configuration file to set our internal state properly. This is a little bit different than just a normal producer-consumer architecture, because a queued message handler allows us to put more than one state onto the queue at a time. For example, if we are using the clock style control, this will queue up two different messages. First, we're going to set the clock style, so let the system know what its internal state should be, and then update the clock style so that the display becomes something different. And here we split up those two operations into two separate messages. Now this might look like a large amount of infrastructure, but there's a nice advantage to this AMC tool, actually several. One of them is if you needed to get a message generator that's located on a host UI and a message processor that's located on a remote target, you have the option of using send local message. You also have the option of sending a network message. And the API for these is almost exactly the same. Pass in the message queue, and here we just also have to let it know what machine is going to be receiving it. The AMC API takes care of the rest for you in terms of getting the contents of that queue across the network and onto the other machine. Pretty handy for that, because it makes a very nice and easy transformation between a local system and a distributed system without a lot of work. I'm always a fan of that. If you want to build your own AMC style applications, we also provide a template. So I'm going to just create a new VI and show you what that template looks like. Oh sure, I'll save my change. So let's create a new VI. Go to the block diagram. And if you navigate to the user library's AMC palette, you'll find a templates subpalette here. You'll also find examples, including the simple clock example I just showed you. Let's go back to the templates though. So here's a queued message handler template. And if you notice, it put quite a lot of code onto my cursor. So let me drop it down. And here you'll see you have almost the entire set of infrastructure for that clock example. All that we'll need to fill in is the details. We're already initializing. We're already getting this event structure set up. We already have the most common cases put in. We can shut down. And over here on the message processor side, we've already pre-populated it with most of the necessary states that you're going to need. Initialize, exit. In our case, we have process data, which just does something. Obviously, you're going to want to add different code here to handle your own cases. And anything that you want, you'll typically just create a new case underneath this. Something else that I recommend doing in all of your designs is have your default case be a missing message handler, where if a string comes in that you were not expecting, have some debug output so you can tell that something happened that you didn't account for within your code. And one of the best things you can do is to actually output. So this inserts whatever string was coming in here, whatever message came in that you didn't understand, it'll put that onto that dialog box for you. Really handy for debugging. So 90% of the infrastructure of the clock example is already here. All the things that you'll need to fill in, of course, are on you, but this will get you a nice template for a user interface style application. Very handy for dialog boxes and things that don't have a large number of UI elements, but you need a quick template to get up and running. Now you can describe how to use the asynchronous message communication reference library for interprocess communication. In the next section, We'll use global variables and single process shared variables for inter-process communication.